with minus 1 in representatives of the cosets. So, for example, if we had, let's say a n x to the n plus da 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 plus a2x squared plus a1x plus a0, plus, and I'm going to stop writing x squared plus 1 and write a instead because I get tired of writing the bracket x squared plus 1. But so this is equal to what? Well, it's really, really complicated. But if you look at it, since we can collapse x squared to minus 1, what is this looking like? Well, it's looking like, I guess it depends on whether...
Oh, are you saying that like every other term?
Yeah, instead of doing n here, let me say this is 10, just for the sake of specificity.
No, I get what you're saying. X squared would be negative 1, so you get minus a2, and then the other one would be like x minus x a3.
Yeah, so this is like a10 times minus 1 to the 5th, right?
Yeah.
a8 minus 1 to the 4th. a6 minus 1 to the 3rd. a4, why did I do 10? a4 minus 1. Right? A0, all of that, and then plus x times, a9 minus 1 to the 4th plus a7 minus 1 to the 3rd. a5, why did I write this out? Idiot. Idiot. All right, all of that plus a, right? Because that's just the representative. The point is there is like some number b plus, x times, we'll say b1 plus x times b2 plus a, right? And I've written this monstrosity out for 10, but you could just as well do it for n. The point is, without loss of generality, if you have f of x plus a, you can rewrite that as something like a plus bx plus a, right? You can always collapse everything, all the higher powers down into just the constant term and the linear term, because we have this identity that x squared is minus 1, right? So, great. And so, look at what happens. If you have a plus bx plus a, right, times c plus dx plus a, you multiply these cosets, how does it work? What does this look like? What's going on here? Well, the rule is we multiply the representatives, right? That's the definition of the multiplication and the factoring. And multiply that out, what you got? Well, you got AC plus BDX squared plus AD plus BCX plus A. But x squared was what? X squared was minus 1, right? So this is AC minus BD plus AD plus BC times x plus A. What are we looking at here? Well, if we just change the notation a little bit, maybe you can see what we're doing. Right? Change the notation ever so slightly, and it should become clear what we're looking at. See, if instead I had written a plus b I times c plus di, and I multiply that out, and I get ac minus bd plus I times ad plus bc, you'd recognize that as complex number multiplication. But that's exactly the pattern we have here. See, so what I'm saying is that one model for the complex numbers, or that the complex numbers are the real polynomials mod the ideal generated by x squared plus 1. We can build complex numbers as a factoring in this way. I think this is one of the more elegant ways and beautiful ways of constructing the complex number systems. But it does come at a cost, right? Yeah, 2x2 matrices are much more accessible to, say, high school students, right? So that brings us to the next section, which is on prime and maximal ideals. So let's get into it. Definition. R, commutative ring, and a proper ideal. Ooh, now watch out for that, right? Proper ideal of R. Number one, A is a prime ideal. All right, of R. If what? If A and B in R and AB in A implies A is an A or B is an A. And then two, A is maximal ideal, all right, of R if any ideal B of R with A subset of B subset of R has what? Has either B equals to A or B equals to R. So that's a prime ideal, that's a maximal ideal. So what do you think? Is the ideal generated by a prime going to be a prime ideal? I bet it's going to be, right? So let's let P be prime in Z, yeah? And consider PZ, which of course is the principal ideal generated by P, right? I say if A and B are integers, all right, and AB is an element of PZ, then what? Then that means AB is equal to PK for some K, right? Integer K. What does that mean, though? Well, that means P, thus P divides AB, right? Is that right? Well, anyway, of course P divides AB if it's a multiple of P, right? So we have a prime divides the product of A and B. What did we learn about that? We learned that that implies P divides A or P divides B, right? That was called Euclid's lemma, right? And so if P divides A, that means A is equal to Pn, or B is equal to Pm, which means A is in the ideal generated by P, or B is in the ideal generated by P. So apparently, a principal ideal generated by a prime is in fact a prime ideal. to understand maximal ideals, I think it's useful to draw a lattice diagram. This is probably where we'll end class with this today, I think. So we're almost done here. This is one of those things that I'm guilty of in my abstract algebra teaching, of not emphasizing enough. And real algebraists do a lot more with these pictures than I do. But here it is, Z36, right? Which of course we recognize as Z mod 36C for what it's worth, right? But inside here, you have the principal ideal generated by 2, and you have the principal ideal generated by 3. And then below that, you have the principal ideal generated by 4, and when you look at these two together, you get these guys. And then there's 9 over here. And then put these two together, and you get the principal ideal. I'll try to explain more what this picture means in a second. So let me finish drawing it. And then finally 0 down here at the bottom of everything. So the ring, if you will, is up here, all right? In this, and like the ideal generated by 2, how many things are in there?
Ideal generated by 2?
Yeah, here, the ideal generated by 2, it's got 18 things in it, right? It's basically the evens. The ideal generated by 3, it's got 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33. There you go. It's got those 12 elements to be explicit. And of course, to be more explicit, those are residue classes, mod 36. But anyway, the point is, these two guys are maximal. Because there's no other ideal that you can, if you put an ideal between them, that ideal either has to be them or that. There's nothing else. So the maximal ideals are 2 and 3, right? And here's the thing. If you look at Z36 mod 2, right? There are just two things in that, like the evens and the odds. So this is isomorphic, in fact, to Z2. And similarly, you can argue that Z36 mod 3 is in fact isomorphic to Z3. I know there's 3 things in that because I know that there's 12 things in the coset, and so it partitions Z36 into equal sized bits. There has to be 3. Likewise, there has to be 2 of the thing that has 18 in it. Now, in contrast, right? Now, those are fields. Those are fields. So this illustrates a theorem, which is that a ring mod a maximal ideal is a field. These are examples of that. What if you don't have a maximal ideal? Ring mod an ideal which is not maximal. Does it have to be a field? Well, it turns out no. So like this thing with 4 in it, I think there's 9 things in there. So I believe if you take, now I'm pretty sure this mod that is isomorphic to Z4 actually, which of course is not a field, you know. Now, I will say this. We know that the complex numbers are a field, right? So you might wonder, in my previous example, can we prove that the ideal generated by x squared plus 1 is a maximal ideal.
So, is it an if and only if?
Ah, is it an if and only if? Good question. Let's see here. Well, my next example past this one, the one I won't do today, I give proof that the ideal generated by x squared plus 1 is maximal in the ring of real polynomials. And then I kind of give a counter example to that, looking at it in Z2x. And then theorem, 4.3.6, let R be a commutative ring with unity, I an ideal, the quotient ring, R by A. By the way, the factor ring is also called the quotient ring. The quotient ring R by A is an integral domain if and only if A is prime. So it turns out prime ideal gives you a factor ring, which is an integral domain. Right? And it goes both ways. It's if and only if. And then, yes, you're right. Theorem 4.37 says let R be a commutative ring with unity. Let A be an ideal of R. The quotient ring R by A is a field if and only if A is maximal. So in that sense, the example 4.34, which we'll look at next time, will be supplanted if we already knew the complex numbers were a field. See, the fact that the quotient ring of real polynomials by x squared plus 1 is a field shows that the ideal generated by x squared plus 1 is in fact a maximal ideal. And that theorem gets used both ways. Sometimes it's far easier to show something's a field than it is to prove maximality of the ideal, you know. But those are the two big theorems in this lecture 22. I'm trying to get a little bit ahead because at some point I have two things in one day, and I've got a blurb in there somewhere. So I'm trying to edge my way. So I'm a little bit. So hopefully next time we meet, I'll finish 22. Finish 23, lecture 23, and get a ways into 24, something like that. That is my intention. What do you think of the take-home test?
I haven't looked at it yet.
Haven't looked at it yet. Oh, it's no fun.
Yeah, the
It's harmless.